Hi and welcome to Redeye. With me today I have Per Woxenius, Head of Product Management at Freemelt. Welcome, Per.
Thank you.
So today we're going to take a deep dive into Freemelt's focus industries, defense, energy and medtech. But first, please tell us more about your background and your primary responsibilities at Freemelt.
My background, I have a solid engineering background, and I've worked most of my years in manufacturing technologies. Worked in ABB and hot isostatic pressing, hipping, which is one part. Subsequent part of this, I worked electronics production. I worked at Arkham as VP R&D. I worked with GE Healthcare, working in medtech as VP R&D. And I worked at JKN Aerospace as a program manager, working in the research field. So I have a very mixed background, but always in engineering, always in developing products. So that in short is my background. At Freemelt, my role is I am head of product management. It entails two things. One is a product management, what we should do, which product should we develop, but also the development of the product itself. So it's a combination of both. And what do we develop? We develop 3D printers, and it's sort of, most people know about 3D printing, but we are, in a sense, quite niche. We work on 3D printing in metals. We focus on tungsten, titanium, and copper. And we use an electron beam instead of laser to melt material. And why do we choose lasers? Why do we choose electron beams? And that really comes down to productivity. First and foremost, productivity, but also that you can also design material properties in a much better way. So again, the productivity and ability to tailor material properties, which are great benefits.
And how does the traction look like when it comes to electron beam versus a laser beam?
Electron beam is definitely the smallest, but what we can clearly see, and which I think is really encouraging, is that we have more and more players coming into this field. Because being alone or being just a few companies, I think that sort of shows that you're doing the wrong thing. But when we see companies coming in, entering the space, I think that is really good, as long as we can dominate or have a very strong market within it.
And you launched your 2030 strategy in the summer of 2023. Mm-hmm. And I mean, what are the key elements of this strategy, and how do you plan to accelerate your commercialization of your product and service portfolio?
So again, the 2030 strategy, we have a goal to have a turnaround of about 100 million euros in 7 years' time. And of course, we have to build an organization to do that. And what we've done lately, I think most interesting, is really the commercial development in the US. We now have 5 people working there, both in service and we have application development, but also people really specializing in defense, specializing in energy, and of course, sales couples of that. So that is really interesting. So what I can say, of course, development will still be important, but the share of a part of a company will diminish. We will also grow, but other parts of a company will grow more, like the EMEA organization in the Netherlands, like the US. And again, coupled to that, we have to, of course, to develop the right products and the right offerings and the right service, and these systems are made to be used for a number of years. And of course, also the service organization and all that type of work that needs to work well and also give us an income, of course, through the full development cycle and life cycle of a product.
And I mean, your ambition is to establish Freemelt as a market leader within the electron beam space, so to say. And here we're with focus on defense, energy, and medtech industries. And here we aim to be a leading partner by generating increased productivity, reducing operating cost, and maximizing long-term customer value. And if I understand it correctly, you have currently most momentum within defense and energy.
Correct.
But can you elaborate on the growth potential in all these 3 industries, and maybe what are the main revenue drivers in the coming years?
If you look, let's start with defense. What we can clearly see in defense, and as we all know, that there has been such geopolitical shifts in the last 2 or 3 years. Everyone knows about Ukraine, of course. What happened there, that is for us, obviously, we have become NATO members because of that. We have increased cooperation with the US and Europe, etc. It is obvious for us, but what we tend to forget in Europe and Sweden is what has happened before. When it comes to defense, I would say it's more important what's happening between the US and China. because the US has to bring, and also we have to bring back competence, we have to bring back production to Europe and United States, because we cannot rely on China. So that is, it's not only Ukraine, it's also China. And if you look even further back, the COVID crisis a few years back, which really interrupted all the supply chains, that also was really, really important to understand, both for defense, but also energy and orthopedic implants, that we have to bring back the full supply chain to the West. So that is, I would say, drivers for especially defense, but also for energy.
And you're talking about local manufacturing. How
Yes.
does 3D printing play a part in that?
I think it's really, really important to be able to do that, because what really all you need, of course, you need energy and you need powder. You need, for example, tungsten powder, titanium powder. That is really all you need. So you pile up stock, which is just the powder, not the specific part itself. And I actually sometimes compare to Zara, the fashion company, because what they do is they make T-shirts somewhere in Southeast Asia, but they're white, just plain white. They bring them to Spain, and depending on trends, they do all the printing and everything. And they don't sell anything on discount almost. If you look at H&M, they do everything ready in Southeast Asia, wherever it is made. They bring it here, and they have to buy it much earlier, they have to sell much more on discount. So if you compare with Zara and T-shirts, and you look into 3D printing, you just have powder, and of course the energy to melt the powder. So that really changes the supply chain totally. And we can source powder in Europe, we can source powder in the US or wherever, and we do that with partners like Sandvik.
Interesting. And if we move to energy and the growth drivers there.
The growth there is something everyone talks about, climate change, definitely climate change. And I just read this morning, actually, a paper that most people think like 10 or 15 years away in time, that is when you have peak fossil fuel. But actually, IEA and International Energy Agency, they predict that next year is peak fossil fuel. From then on, we will reduce the use of fossil fuels. And that comes from solar, that comes from wind, but it also comes from nuclear power and what we believe in the future, fusion power. And the future is actually quite soon in fusion power. We're talking about being on the delivering power in 10 years' time, which is soon in this type of field.
And what kind of materials are we talking about when we're talking about fusion energy?
Tungsten, purely tungsten. I'm not going to be too technically detailed here, because this is sort of very, again, niche. But in general, what you do in fusion power, you heat a plasma, a gas up to 150 million C. And of course, no materials can withstand that. But the radiation from it, you need material that can handle high temperatures. And I've tried a number of different materials in different tokamak fusion generators around the world, and nothing really seemed to work but tungsten. So where we've tried other materials, they tend to move towards tungsten. In the US, in Europe, and Korea, they go to tungsten. And that is a material which is very, very difficult to produce, really difficult to produce, because it has a very high melting point. And I usually compare with the melting point is 3,400 C, and there's no other materials will have a higher melting point. So I usually compare, it is like boiling water in a kettle made of ice. The kettle melts before. So there are no really good methods to produce tungsten and except 3D printing.
And are there any difference between a laser beam here and electron beam?
Oh, thank you for asking. That's a very good question. The laser beam, the problem with that is because you have such a high temperature, you have a temperature decreases so quickly, the material cracks. You can only make thin-walled products. And what we can do, we can make dense products that don't really look much, but we really do the work that we should do. To make dense parts in tungsten that doesn't crack. And again, we can also tailor material properties, grain orientation, and all the technical details. So I would very simply put, lasers doesn't work. EBM works.
Interesting. And if we move on to medtech, what are you seeing there?
In medtech, again, getting boring here, tungsten again. You can do in tungsten, you can do like something called collimators. This is a collimator, a part of it that you can do. What does it do? It really directs, this is for X-rays, you can direct the beam. So this is something that you can do productively. But when it comes to medtech, titanium is much more important. It's a much bigger market, and it's also a market which will come earlier. So if you look into orthopedic implants, that is what we are discussing. There is about, I believe, 7 million implants being made every year. 96% is made by traditional methods. Only 4% is done by 3D printers. But this market grows 5% per year, and also the part made additively increases. And we believe in 2032, 20% of all implants will be made in 3D printers. So there will be at least 5 times as many 3D printers in 5 years' time, or 7 years' time.
And you have also announced orders connected to these industries.
Yes.
And maybe if you can take us through some of the specific customer cases that you have announced. For instance, UK EA in energy, Saab in defense, and maybe some projects in medtech.
Let's start with UKAA. The UK loves long abbreviations. This is United Kingdom Atomic Energy Authority. We have done a feasibility study for them and with them last year. And what they want to do, they work with fusion energy, again, fusion energy. What they wanted to do is to see if our technology works for tiles within a fusion power plant. So what they wanted to test was, of course, when you talk about 3D printing, you think about the machine itself, but really in this case, they wanted to evaluate our software, the way that we melt materials. We can move a beam more than 10,000 times per second. And the benefit with that is that you can tailor material properties, and you can also melt very productively. So we did a study for them. We did what we called low power melting. For us, it is still 10 times faster than anyone else has done in the world. But for us, it's low productivity. We did this study for them. And all this material, all the studies has been evaluated by them, and they will publish it, we believe, in the second half of this year. It will be fully public information. I can't disclose what it will say, but I'm looking forward to it. I'm really looking forward to it because we know that we have really done well. We can see that we have something. So we have, again, tested the way that we melt material, the way that we can create microstructures, etc. The second study, I think, is even more interesting. 2 things. One thing is, UKA is driving this, but the financing comes from, it's called Eurofusion. And that is the same organization that builds ITER, a fusion reactor in France. So we can see that we have more people being interested in what we are doing. What we'll do there is to evaluate high power settings. Then we'll become, we believe, 5 to 7 times faster compared to what we are today. So we can really melt very quickly. And you look into this, because quite common, we talk about misconceptions in 3D printing. If you talk about this, again, we heat up to 3,400. See, the melting phase, there are a number of steps when you do this process. But when you do the melting, it takes 2.3 seconds to melt the top layer. And at that phase, we in this case, 3,600 holes at the same time. So this has really created a buzz, I would say, in this community, because we can show that we can tailor material properties, we can show that we have very good material properties, and we can show it that we do a high productivity. And I can clearly see when we present this to different organizations, we get calls straight away afterwards. We get champions within the company. They want to say that I found Freemelt. So it's really encouraging when we go up to meet different organizations.
And if we move on to defense.
Yes.
And Saab.
Defense and Saab. That's when it becomes tricky. We can't say too much, but we do a feasibility study with Saab Dynamics, where we present results. I can't tell you about materials. I can't tell you about anything. But I think it's really encouraging that we work with Saab. But I would also say that this is not the only defense company. We also do application studies for American companies. We also do feasibility studies for American companies. And it comes down to, in this case, it usually is, again, tungsten, because it's a material withstand high temperatures, but also it has a very high density, which is also good in military applications. And we have also we have a person in the US employed to work on defense. He has a background in the Marines. He has worked with another 3D printing company. He built, I think, $100 million business in the US. Then he decided to do something else, has joined us. And it is really interesting to see how quickly he interacts with the US companies and also within Pentagon, etc. And that sort of gives us a very good chance to come in and again do feasibilities, do application studies.
And before we move to medtech, maybe if you can describe the difference between working with a private player like Saab, and you have other players, private players, and an authority like UK AEA.
It's very simple, speed.
Yeah.
Very, very simple. How quickly do we act? It is a big difference. And again, also you can see how quickly you act in the US compared to Europe. So you see, and if you look into defense, I was listening to FMV, the Swedish materials procurement agency. They said we thought we had eternal peace. We wasn't in a hurry. Now we are in a hurry. And if you look into FMV in Sweden, in 2021 they bought material for 18 billion SEK, the year after 36 billion, the year after 54 billion. So they are really in a hurry to buy material, buy munition, and buy new material. And of course, that is also important for us to see how quickly this market grows and how urgent it is. Because what we are doing, we are depletion in munition in Ukraine. We need to get new munition, new weapon systems, etc. And that is all over the world.
And lastly, do you have any customer cases within the medtech industry to share?
No, not really. Sorry, that was a blunt answer. We definitely work with some of the major implants companies. We develop and look into the parts we do. And when it comes to the Freemelt ID, the Freemelt system that we have developed for 3 years' time now, from day one, we had an implants company working with us. So, of course, we work with implants companies, but I can't disclose which one it is. So that was the reason for my blunt answer. But again, if you look into this, this is an orthopedic implant. It's a hip cup. It is put here in the leg. If you implant, it's about 2.5 million implants being done every year. This is something we have done for an implants company. To work on this, being able to stack parts in a machine to build part productively. So this is a typical application for implants. This is something that we develop with implant companies, but I'm not going to say which ones it is. So we work on primarily what is called large joints, knees, hips, ankles, shoulder. That is sort of a product that our customer looks into, and we look into using our products.
And why is 3D printing so suitable for implants?
It is really coupled to the freedom of design, being able to combine solid material. Like we talked about large joint, it's sort of like a hip, so it has to be solid somehow to have a movement, to take it millions and millions and millions of time. But on the other hand, you also want the porous structure. This really mimics the bone. You might think the bone is solid, it is not. It is porous on the inside. So there is sort of rules how you should make this type of implant so that it should fit the bone. Porous about 0.6 millimeters, struts about 0.4 millimeters. This is easy to do in a sense. And when it comes to the design that the customer wants. So combine this, and when you have the bone ingrowth, you can have a part growing into it, and this stays forever. It stays very, very well. I think I would like to add a misconception when it comes to orthopedics. People think that you also have special implants, special for like a skull implant or for the knee or whatever. That is quite unusual. The most common ones are standard products that you do day in and day out. You make the same things in the same printer for 20 years. So you buy a printer, use it year in and year out. And then when it becomes important to be a productivity partner, as we call it, we sort of develop a processor, it goes quickly, you can produce quickly. But when you produce it in the same system for 20 years, you have a maintenance on it, you have service contracts on it, you have income for many years on the system. So I think it's important to show that when it comes to implants and other markets, that you get income throughout the product's lifetime. And in 20 years' time, hopefully you build the same implant 20 years straight.
Yeah.
Boring, but it helps
good
many
for
people.
business.
Good for business and good for customers and patients.
Yeah. And maybe if you can expand on Freemelt's unique selling points for each industry, and maybe if you can elaborate on the difference if the customer have a traditional manufacturing method today or a competing 3D printing method.
Yeah, I think it's very good that you mentioned traditional method, because we really, really want to look into competing with traditional methods. As I said, our orthopedic implants, the growth of traditional methods is faster than 3D printing growth. So we want to get into that. So the unique selling points for 3D printing, not only Freemelt, but 3D printing in orthopedic implants, is the freedom of design, to build a porous structure, couple that with solid structure. So you can have bone grow into it, so it gets stuck. and having this. So what the benefit is that you have a much longer life, and you also have a high survival rate. It is the risk that the implant fails is half as much in the 3D printed implant compared to the traditional one. So that is the unique selling point for us and for the 3D printing community. Our USP, again, in orthopedics when it comes to productivity, so being able to do it at as low cost as possible. If you look into energy, if you look into defense, it's different when you look into tungsten, because we do things that no one has done before. No one has done what we're doing. Making parts with high material quality and making parts with high productivity, and really, really competing with traditional methods. So the unique selling point there is, again, you can do things really quickly, and again we see the response we get when we show what we're doing, when I show how quickly we can do things. So being able to do things with much higher design, freedom of design, much higher productivity, and rather much lower costs, and you couple that with superior material properties, that is really a killer application. Something that we can really dwell on. So that comes, I would say, both for defense and also energy sector.
And in terms of traditional manufacturing versus competing 3D printing method, I mean, I guess it's harder to convince a customer that uses traditional manufacturing to go into 3D printing, but maybe if you can elaborate on that.
Oh, you're absolutely right, especially if you work in regulated businesses. So I think if you look into orthopedic implants again, it is 3D printing implants has been done for 15 years now. So it is not such a big thing within that community, because most players have a product line. At the top of the line, they have 3D printed implants, and then it goes down to more traditional, so we can have a different pricing strategy. And of course, we hope that more and more will go into 3D printed parts. And we can also see that, for example, hip cups is quite common, but you can parts for the knee is becoming much more common. More and more players going into that, making both the upper part and the lower part. In this case, also the upper part is because you have material changes, which is much better for the body. It's biocompatible in a much better way. And you also asked before the difference with our technology compared to other 3D printing players. And again, it comes down to productivity. And of course, that translates to cost.
Yeah. Okay, so that was actually my final question. So thank you for taking your time, Per. And thank you for tuning in. Bye.